right, now we're on to electrostatics. We're going to be doing the algebra-based part today. So that means we're doing everything that is not calculus-based. So we're not going to do charge distributions or Gauss's law with this today, but we'll do everything else like force, field, potential, energy, all that stuff. So to start, what's the electric force between two charged objects? Well, of course, that magnitude is given by Coulomb's law. So the electric force is just going to be the Coulomb constant times the product of the charges divided by the center to center distance squared, which will come up shortly. And if for whatever reason you don't like the Coulomb constant K, you can also write it in terms of the permittivity of free space, epsilon 0. All right, what are both parts of Newton's shell theorem? So Newton's shell theorem for electrostatics has two parts to it. It is the same as the gravity one. We know that the force on a charged object in a charged shell is zero everywhere, not just the center. And any sphere can be collapsed into a point charge, pretending all the charge is at the center of the spherical distribution. Assuming there's that symmetry there and we don't get some very odd charge density that it's like the top half is more dense or something, but you won't see that. So any sphere, just automatically shrink it to a dot. Just making sure to respect that sort of radius of the sphere if you have to. So what we mean by the first part is the first part says that if you're inside a charged shell, meaning this shell might have charge Q on it, if you are anywhere inside the shell, even if it's not the center, the electrostatic force is zero on any object inside the shell. And we reasoned through why this was, because even though you are experiencing a force from different parts of the shell, the fact that you're closer to this portion of the shell is exactly canceled by the fact that this portion of the shell has sort of a larger area where it's a squared versus inverse square relationship, so they cancel. Now, this one is harder to prove without Gauss's law, that any spherical distribution can be modeled as a point charge. So let's say we have a solid sphere of charge plus Q. Well, this means that this electrostatic relationship, if you want forces or anything like that, it's actually just equivalent to just pretending the sphere isn't there anymore and just collapsing all the Q to a dot right at the center. So that's what the second part of the shell theorem says. Usually when we talk about shell theorem, we really just mean the second part right here. That's the collapsing part. That's used all the time. So here's a pretty representative example. Two spheres have radius r, and their surfaces are separated by 2r. And we want to find the force between them. So first, using the shell theorem, draw an equivalent setup using only point charges. So again, anytime you have a sphere with electrostatics, you can just pretend it's a point charge. Just remember to get all the lengths correct. So this says that we can shrink down the first sphere and say it is just a dot with plus Q at its center. We can also shrink down the second sphere into a dot plus Q at its center. And we knew beforehand that the surfaces were separated by 2r. But that's not going to be our charge separation, right? Because we just shrunk them down to point charges. So this extra space, that does exist, and that is going to be important. So we shrunk down the sphere, so that means there's a radius of the sphere here that gets tacked on, and there's a radius of the sphere here that gets tacked on. So this will be helpful for later to note that this sort of distance between the spheres is now 4r. Now what's the net force? Well, Coulomb's law says it's just going to be kq squared over r squared, where r is the center to center distance. That's why we use the center to center distance. It's because of the shell theorem. So it's going to be kq squared over the distance is 4r. And be careful with our parentheses here. Make sure we're squaring the 4 and the r as an entire object. So 4 squared is 16. So we get 1/16 kq squared over r squared. And I didn't ask it, but the force is always going to be the same between these two charged spheres, no matter what's going on with them because of Newton's third law, equal and opposite reaction. Now I got three charged spheres. This is a vector problem. So we did like a simple two-sphere example. Now we'll do a vector example. Three charged spheres are an equilateral triangle, side length L. Draw the individual forces on the top sphere. So we're going to be interested on this guy. I guess. This is a gendered sphere apparently. All right, so top sphere is positive. So we're going to get some sort of a repulsive force from the blue sphere. And then this sphere down here is negative. So the negative will attract the positive. So we get a force like that. And all things are the same here. So I'm going to try to make my vectors sort of the same just so we can easily see what's happening. So I might make this force up one, right one, and I might make the other force down one, right one. So we see that what's going to happen is by symmetry, if I can actually draw an arrow. So now we can see by symmetry, I'm not going to draw it on here. Don't put net force on a force diagram. Like, this is not a real force. Net force is not real. It's not a type of force. It's really just an adjective. We see that we are going to have a rightward net force this way to the right. So now that's the task, really, is finding this net force. This is a pretty standard problem. Suppose the top sphere is mass m. Derive an expression for the magnitude of the initial acceleration. So we don't quite want the net force. We want the acceleration, but it's essentially the same, right? Because Newton's second law says acceleration is just our net force divided by the mass. Because that's what forces do. They cause accelerations. So we just need to find the net force. Now, to do that, this is, of course, a vector component problem. And the fact that this is an equilateral triangle means that our relevant angle is 60 degrees. Because a triangle has 180 degrees, and we're equally splitting the angle three ways. So what is causing the net force? Well, the net force is caused by two charges, but not all of the force from the two charges, just the x component of the force from the two charges. And due to the fact that we're defining our angle as this polar angle, we can find it just by taking the magnitude of the electrostatic force and multiplying by cosine of 60 degrees. Because again, if we define our polar angle like this, we can associate the horizontal force with being adjacent, right? If we draw just a sort of right triangle, we see that the horizontal leg would be touching the 60, so that's adjacent. So I'd use a cosine. Force between two charges is kqq over r squared, where r is the length L in this case, and cosine 60, that is actually just 1/2. So we get this sort of counterintuitive result that the net force is actually just looking like the net force between two charged spheres separated by L. And I guess that should make sense here because exactly half of the effective force is being directed to the right from each sphere. So you get sort of the net result as being just 1 kq squared over L squared. But that's not quite what we wanted. Acceleration is F over m. So we get kq squared over m times L squared. Now its acceleration will definitely change over time. It's going to have a decreasing acceleration as you get farther away. Although this one is not really trivial to analyze because it's not going straight up. It's an easier analysis if you do both plus q's. But pretty straightforward. This is a vector component problem. All right, now on to E field. What is the E field? Well, we kind of talked about this already with circuits. We needed this idea. The electric field is force per unit charge. So it's really the direction of force a positive charge would feel if you place it at that location. Positive charges are sources, negative charges are sinks. E field lines cannot cross because that would mean you get two forces at the same spot, which clearly can't happen. A lot of times why we use the electric field is because the electric field exists no matter what charge you put there. So we can easily find the force on whatever charge we would like using the relationship electric force is equal to whatever test charge you place at that location times the electric field strength due to all other charges. And as a result, we see that if you plug in a positive, you get two vectors that agree, and if you plug in a negative for Q, you get two vectors that are anti-parallel. So that's telling us positive charges go with the E field, meaning they experience a force along the E field, and negative charges accelerate against the E field. So positives like to speed up with the E field, negatives will speed up in the opposite direction. Now we're just going to draw some E field lines here at the different spots. So just some vectors here. So we know that my plus Q is a source, so really close to this, really close to the plus Q, it's probably going to look something like this. And really close to the 2Q, I don't know why this one didn't go on. And really close to the 2Q, it's going to look something like this. So when we superimpose the two fields, it's going to look like some combination of this with the 2Q sort of dominating. So clearly at B, due to symmetry, it's not too hard to tell that that E field is just going to point to the right, source and sink. And just as a reminder, because I covered it up, this is plus, and this is minus, minus, just to show it's more negatively charged. Then at A, I know that my positive charge is trying to push me away, and I know that my negative charge is trying to pull me towards it. But also that negative charge is going to have a larger pull because it's a bigger charge. So it's going to be pulled down and to the right, but sort of more down. So it would be more down than right. And then by symmetry, C would look pretty similar. So it could be something like this. So if we tried to map out like an E field line, maybe it's something, maybe we get something kind of like this as like our E field line. So it's sort of like a dipole, but it's not going to be as symmetric as the original one due to these charges being unequal. Now I got some force balancing. A small sphere has mass big M and charge plus Q. It's suspended from rest by a string. There's a uniform field E in this region. We want to find the tension in the string for these different orientations of E. Okay, so first, what we know is going to happen no matter what is we know that the sphere has weight, so there's going to be a gravitational force, mg, that's straight down, and there's going to be a tension force, ft, that's straight up, unless if we're moving the sphere horizontally. So there's always going to be some sort of mg down. We know that's true. Now what's going to happen with the electric field is it's going to exert an additional force depending on what direction it is. We'll see it makes our force diagram a bit different. So first, we have the electric field oriented down. So the relevant equation here is that the force is equal to charge times the electric field. And since this is a positive charge, the force will be with the field in each case. So if we do that, making my dot big because I'm going to need a couple forces. Not only do we have the weight of the sphere down, we also have an electric force down because this is our E. So we get an additional electric force, QE, down. So our tension force, Ft, must balance both of those put together. And since this is balanced, I call this a Newton's first law equation, not a Newton's second law equation, where we say that the force up, Ft, has to exactly balance the combined efforts of mg and QE. So this is a case where eventually you could be pulling too hard on the string and you could snap it. That's kind of your limiting factor here. If the E field is so strong, the rope could not support it. I'm just being a copy paster here. All right, now if we do the E field up, what is that going to do? Well, no change to mg, but there will be a change to Fe, right? The electric field is now going to exert a force up. So that means tension is actually getting some help. So now when we do our force balancing, our upward force, tension, and the electric force together need to combine to balance the weight. So the fact that we've given the tension force some help means that tension doesn't have to balance the full weight anymore. It has to balance the weight minus whatever help it has gotten from the electric field. In the limiting case here would be if QE equals mg, you can actually get the sphere to be sort of balanced by the electric field alone, and it could be potentially just pulled up without the string. And now here's an interesting one. The electric field is oriented to the right. So if we're oriented to the right, that means the string itself is going to get pulled to the right a bit. So our picture actually changes here. This is going to change our picture because now what we get is our sphere is going to get pulled. And if we look at our forces now, there's still going to be its weight, mg, that pulls down. It's still going to get pulled by the electric field, or electric force rather. That QE force is just going to be to the right now. So that means tension is sort of at this angle. So it becomes a bit more complicated to think about exactly what's going on in this case. But when we shove everything in a triangle, it'll make a lot more sense. And sometimes you can do a pretty complicated variation of this where we do some math, sort of finding this angle theta, which we might talk about. Yeah, we'll do that at the end. So if we actually look at our force diagram, we can put these in a triangle together where Ft is an angled force, mg is a vertical force, and QE is a horizontal force. So what do we notice about this? Well, it's a right triangle. So Ft, the length of Ft, has to be whatever the hypotenuse is of this triangle, because the x component of tension has to cancel QE, and the vertical component of tension has to cancel mg. So we can just write a Pythagorean theorem relationship that Ft is equal to QE squared plus mg squared. And another thing that can come up with this problem that is pretty common, I know it was on the FRQ in like 2023 or something like that, is this relationship that the tangent of the hanging angle is QE over mg. And that comes up because the trig function uses tangent here because we usually don't know anything about tension. So usually you can use this as a lab. I know I do it as a lab to try to calculate the charge on two spheres using this principle. So now we got some superposition. This is again a classic. We'll see this is pretty much like the triangle version with Coulomb's law. This is pretty similar, where we have these two charges that are placed symmetrically. And we're going to be interested in finding the net field somewhere along this axis. So again, it's superposition. So these are both sources because they're positive charges. So I'm just going to draw field lines that point away from each. And we see that by symmetry, once again, we get a cancellation and we get a net force that's purely along this axis. So that means the vertical components are going to cancel, the horizontal components are going to add. So what that allows us to do is we can say that our net electric field comes from two charges, but not all of the field from two charges, just the x components once again. So we'll see this is pretty similar, except there's one like major change with this. And we know that if we define a polar angle, we can just get that by multiplying by cosine of theta. And that's why this one is different, because we don't actually have the angle theta. We know stuff about the triangle, though. So if we create a triangle out of this, I'll just redraw it. We are looking for the electric field strength, and that's an awful triangle. Wow. Maybe we should do the hypotenuse last. Yeah, that makes sense. So we are looking at our two charges. This is our x-axis right here. So we're looking at one of these charges is up here, so that's going to be displaced a distance a, and we're a distance x along from the origin, because again, there's another charge that lives down here somewhere. So that means that we're going to define our usual polar angle, theta, over here. So the distance to the charges is just given by the Pythagorean theorem. So that means when we do our expression for cosine theta, the electric field from a point charge, well, electric field is defined as force per charge. So it looks like, so the force would be like kqq divided by r squared. But we're not looking for the force, we're looking for the force per unit charge. So we take out this test charge that we don't know what it is that will be placed there. And now we just got to do some substituting. So again, r is the distance between the observation point and the charge generating the field. So that distance is going to be the Pythagorean theorem distance. So that's the one that gets squared. And then cosine is defined as the adjacent side, so x, because that touches theta, and then the hypotenuse. So now we can just simplify. So we get 2 kqx on top, and then on the bottom, we get, well, 3 copies of the Pythagorean expression. So we have x squared plus a squared under a square root, and that's cubed. So since we're cubing a square root, that is equivalently a 3/2 power, because the cubing is the 3. Oh, the cubing is the 3, and then the rooting is the 1/2. So this is a pretty standard derivation. You can imagine there's other iterations of this where you need the other component, and you'd get something like kqa, 2kqa over x squared plus a squared to the 3/2. Notice this makes sense because this tells you if you plug in 0, that's always a good idea. If you're doing something where you're deriving a function, plug in 0 and see if that works out. If you plug in 0 to this, that would mean what is the field right here? Well, I'm going to get 0, and that makes sense because the sources and sinks are going to exactly, or the sources are going to actually compete, exactly canceling at the origin. So it does make sense that we get the x on top and not the a. So if it's ever a multiple choice item, you can kind of discern what the answer is. Because if you do enough of these, you see the 3/2 thing shows up all the time. And you're going to get either like an X or an A. So you can figure out which one it's going to be by determining, like, should the field actually cancel at the origin or not? So that was my 2 examples for field. What about potential energy? So how do we define electric potential energy? It's defined similarly to the planet version of gravitational potential energy, where it's the amount of work required from a force to assemble a group of charges. So it's how much energy you need to gift a charge distribution to make it appear. So for 2-point charges, it looks sort of like Coulomb's law, except there's 1 power on the bottom, and it's not a vector, it's a scalar. And because charges can be signed, that means that energy can also be signed. So we don't mess with signs with force or field because it is a vector. Vectors don't have signs, they have directions. But electric potential energy and electric potential, those are numbers. And numbers do have signs. So we respect the charge signs here. So electric potential energy, when is it positive? Well, it's positive whenever I multiply these 2 numbers together and make a positive. So how can you make a positive? Well, it's positive, positive, or negative, negative. So 2 charges of the same sign have positive electric potential energy. And we can interpret that as saying it costs you energy to bring charges together. So if you have charges that are far away, there's going to be no energy initially. And then if you bring the like charges together, they are going to have potential energy. The system, the two-charge system, will have potential energy, and it's positive at the end. And that is representing that it costs you energy to bring positive charges together because they're not happy about being brought together. You have to pay them to bring them together. Now we can see the sort of inverse of this. So for negative charges, or sorry, for two charges of this opposite sign, that potential energy is negative. And you can think of that as this idea of being an energy debt, where instead of thinking of the energy sort of associated with bringing them together, which does still work, which I'll explain in a second, you can think of this as like being an energy debt, where this is the amount of energy it costs you to separate them. So instead of talking about bringing the charges together, you can also talk about separating them, because these charges do not want to be separated because they're going to be bound together. So this is the amount of energy you need to pay to free them from their energy debt. Now, why is it negative if we use the bring them together definition? Well, if you bring negative charges together, or opposite charges together, they are going to try to accelerate towards each other. So they're trying to accelerate, and you're really just pulling on them to prevent them from just speeding up and smacking into each other. So it's negative because you're sort of stealing their kinetic energy that they would have if they're allowed to just fly in together and collide. So that's another interpretation as to why this UE is negative. How does this relate to these sort of works that are commonly asked about? Well, this one is easier to understand. The work done by external forces, this is just how delta U is defined. Because we're always talking about electrostatics, where we're slowly bringing these charges together, and work, like net work by external forces, can be thought of as just the net energy change of a system. So that's just saying, like, how much energy did I have to bring in from the outside? How much energy did I have to bring in from the outside to get these charges together? Because energy can't just come from anywhere, right? This is an illegal bar chart if my system is closed. So there must have been energy that came from the outside, and it did. This external work generated those energy bars. So conceptually, that's why the external work is the same. It's to conserve energy. Now, what's going on with this? The work done by the electric field. Now, the electric field, that is a force internal to the system. And since it's internal to the system, the electric force can't change sort of that total energy of the system. So it's easier to think of the work done by the electric force, which is, we'll just define it here, is the opposite of the potential energy change. This is easier to determine when you sort of look at your energy conservation problems, where let's say you might have a lot of potential energy and no kinetic, and then you release the charges and you get sort of less electric potential energy but more, let's make it look like it conserves at least, and you get more kinetic energy. So I like to interpret this electric field work as being opposite of the potential change. I think of it like bar charts, because what is the electric force doing? Well, the electric force is changing your kinetic energy. It's either slowing you down or speeding you up. So because of that, you can't just gain bars internally from nothing. So if you gain bars from kinetic, if you gain bars in kinetic, you lose them in potential. So I like to interpret it that way. Honestly, you could just use the mechanics version, where if you go with the force, that's positive work. So just think about which way the electric force wants to move you and make that positive if it goes with the force. But I just memorize this, honestly. This is one of the few facts that I think just is worth memorizing. The external force doesn't really involve memorizing. I feel like it's pretty easy to reason that you can't just spawn in energy, so the work done creates that. But this is a fact that I encourage you just to memorize to avoid a headache. And there's not many things I encourage you to memorize. 4-point charges are arranged in a square of side length S. Derive an expression for the net electric potential energy of the 4-charge system. Okay. So the electric potential energy is the sum over all pairs of charges of their relative amounts of energy, debt, or how much it costs. So we're just going to pair them up. So these two charges are plus plus. The pluses are not going to be happy, so that would cost me energy. I'm going to give that like a +1 because it's just S apart. Same thing here. This is also a +1. Now over here, this would be a -1 because the plus Q and the minus Q are an energy debt. They do not want to, they would like to be brought together and would not want to be separated. And then we also get a -1 down here for the same reason. Now we can't stop here. Well, I guess we could, but in general, we can't stop here because we have to go through all pairs. So be careful of this diagonal. So this diagonal would be a diagonal that's in debt, and it's not -1 because they're not S apart. They're a 45, 45, 90 triangle apart. So these two S's actually makes a distance of √2. So this would be like a -1 over √2. And then exactly canceled on the other side would be a +1 over √2. So it actually does end up canceling. So if we work this out, we know the units are going to be kq squared over s. And then we had a +1, a +1, a -1, a -1, a +1 over √2, and a -1 over √2. I did intentionally make this 0, by the way. I considered making it all plus q's. If it was all plus q's, we would get 4 plus √2 as our coefficient. But I thought it was more of a learning experience to show this sort of cancellation. All right, now on to conservation. Two spheres are nailed in place along the x-axis as shown. We're going to say the one at x equals 0 remains fixed. And then the one at x equals d is going to be released. And we're going to be interested in finding the speed eventually at different spots. So let's draw some bar charts. Let's see. First, before the sphere is released from rest. So before the sphere is released from rest, well, of course, they're going to have electric potential energy between them because they're not infinitely far apart. And it's going to be positive because they're like charges. It cost me energy to bring them together. And before the spheres are released, none of them are moving, so there's no kinetic. So my energy budget is 2. 2 positive bars. All right, what about when the released sphere reaches x equals 2d? So we can actually do this quantitatively because we know that electric potential energy is given by, for this system, it's going to be kq squared over r, where r is their center-to-center separation. And if we fix one of the spheres, meaning it's stuck at x equals 0, and release the other sphere, well, if it's twice as far away, it's going to have half the electric potential energy to contribute to the interaction. But you can't just lose energy bars. So if I started with 2 positive bars, I have to end with 2 positive bars. So that means there's some kinetic energy now, which makes sense, right? Because I released the sphere. So I must be tapping into the potential well to give myself some kinetic. And then a long time after we release the sphere, well, what does a long time mean? Well, a long time in this case means I'm going to be very, very far away. And if I'm very far away, I have no potential energy left between the spheres because distance is infinity. So all of my energy has been transformed into kinetic. So this is why I am a bar chart user. It really helps us kind of tell the story of what's going on here. A long time after the sphere is released, its velocity is Vf. Derive an expression for that. So anytime you have bar charts, I encourage you to use this form of energy conservation, because if you drew the bars, that means you at least have an idea of what the energies are in each state. So initially we said there was no kinetic energy, but the initial potential energy between the spheres will be kq squared over d, because it's two spheres of charge q. One's at 0, one's at d, so their center to center is d. And then a long time after, we have one moving sphere, so it's 1/2 mv squared. And our potential energy would be kq squared over their final separation, which is infinity. So that's why this goes to 0. So I'm just going to redo this without it, because we just figured out if they're far, far away, there's no potential energy, because it doesn't cost any energy to have spheres infinitely far apart if they want to be far apart. So we just solve it. 1/2 mv squared equals kq squared over d. Multiply by 2. Take a square root after dividing by m, and we get 2 kq squared over md under square root. Pretty common, pretty standard result here. This is a pretty classic energy conservation scenario we should know how to do. What's the new speed in terms of Vf if both spheres are allowed to move instead of just one? So it's easier to kind of just see based on our expression kind of what's going to happen. So we are going to have the same energy. We do have the same potential energy. Except now what's going to happen is it has to be equally shared among two spheres now. So the spheres have to sort of share the kinetic energy now. So what this means is your kinetic energy gets halved. So kinetic energy, which is 1/2 mv squared, the kinetic energy gets halved. And the kinetic energy gets halved, so that means that our velocity must have gone down by the square root of 1/2, because that gets squared. Now I'll show you, this actually isn't my preferred way of doing this. So we can see the velocity has to be 1 over root 2 is the new speed, which makes sense. It should be lower, because if I have to give my energy to both spheres, it should be a lower energy. This is actually how I'd prefer to do it, which is kind of a sneaky way, but I like it. We derived an expression that Vf was square root kq squared over md. And all we did is we essentially just doubled the mass. That is essentially what we did, is we just doubled the mass that was moving. So our mass got multiplied by 2, so we're essentially dividing by 2 under a square root, so we get 1 over root 2 times the original. So that's kind of a sneaky way of doing it, is seeing that the mass is essentially doubling, which that is accounted for here, where we see that our kinetic energy is getting halved, is what it usually was. All right, potential. What is electric potential? Is it a scalar or a vector? Well, potential, just like field is force per charge, electric potential is energy per charge. And this is a scalar, and we usually interpret this as a height. So just like field is kq over r squared, potential is kq over r, where we just remove one of the q's from the energy expression. How can electric potential be visualized in 3D? Well, we say that V is sort of the height at any given location. So you think about sort of extending the xy plane up a height for whatever the potential is at that location. So we say that positive charges generate hills, negative charges generate valleys. So that means that positives will accelerate downhill. So if we think about what like a dipole might look like in this model, it might look something like this, except they're really more like spikes, where you think about this in 3D, where you get hills and you get valleys. So this would be like a positive charge living there, generating a hill, the negative charge down here, generating the valley. There's a sea level location somewhere in the middle. So we can see now why, like, we're saying that positives accelerate downhill, because if positives create this sort of hill location and negatives create the valleys, and positives like to go where negatives are, we'd see that the force sort of points, the field at least, is going to point sort of down this hill, sending the positives to be with the negatives. What about in 2D? Well, in 2D, we just draw on the heights as sort of these equipotential curves where we give sort of their height. So this would be something like we have a positive charge. This might be something like we draw a circle around the positive charge and say everywhere here has a height of, I don't know, 10 volts. So we just put our height map in 2D. This is really like reading a topographic map. If you've ever done that with hiking, or if you have Calc 3 experience, it's this idea of a level set. How does potential relate to electric potential energy? Well, we have two versions of this. We say that the potential is the energy per unit charge, but what we really use for conservation is this fact that your potential energy change is equal to Q times your potential difference. And again, we use this for the same reason that we use electric field, because the potential will be the same no matter what charge we put there as sort of our energy test charge. So this works no matter what we put there, whereas force or potential energy, you have to have that between two very specific charges. Whereas if I just define the energy per unit charge, I can tell you the energy any charge has just by multiplying that charge by the potential. So we usually use this fact. A sphere with mass m and negative charge negative q is accelerated from rest across a potential difference of script e. Derive an expression for the final speed of the charge. So we just came up with this relationship that delta u is q delta v. But anytime you have energy conservation, we use actually our second form of the energy conservation equation, which instead of saying kinetic plus potential equals kinetic plus potential, we could also instead say that any change in your kinetic energy bar chart must have been given to you from the change in potential. So if you gained kinetic energy, you must have lost potential. So usually we say this for potential because potential is always defined in terms of the difference. So we like deltas here. So our change in kinetic energy would be negative. Our Q is negative capital Q. And our potential difference, it says, is positive script E. So we have gained this much kinetic energy, which makes sense. We should be speeding up. So we can just say that our change in kinetic, which is 1/2 mv squared, minus nothing, because we started from rest, is equal to Q times the EMF. So we get that our final speed is 2Q times the EMF divided by M. So whenever you're dealing with potential difference, you want to use this delta version of the energy equation, because it's easier to talk about changes than absolutes. Now you could do something that looks like this, and you'll see it's equivalent by using U as QV. You'll see it's equivalent because the only thing this depends on is the difference between VF and V0, which is our potential difference. So that's why they're equivalent. Two charged spheres are placed along the x-axis. Assume V equals 0 at infinity. On the figure above, indicate the approximate location in region 2 where the net potential is 0. Justify using the 3D model. Okay. So again, what we can think of here is that this negative charge is going to generate a valley or a downward spike, and the positive is going to generate a hill or a positive spike. And notice that we're really asking, like, where is sea level between the two? Well, it should make sense that we're going to get something that kind of looks like this. So we know the negative, we know that the negative charge is going to generate some spike. And then we also know that the positive is going to generate a hill, but the hill is going to be much bigger. It's going to have a larger sort of region of influence. So I might get this sort of height map. I can do a better job of maximizing the hill right above here. I might get something like this. And it's still not great. I think third time will be the charm for my potential drawing. I'm just going to start by making a very large sort of hill, and then I'll make it decay. Maybe something like that. That's better. So we can see that we're sort of getting a valley, and then there's like a large hill, and there's going to be some sort of crossing point, but it should be closer to the minus q charge because the influence of the hill is greater than the influence of the valley at the midpoint. So at the midpoint, we are going to have like some positive height. All that is to say, the location is in region 2, closer to the minus q. The minus q generates a valley. The plus 4q generates a hill. The hill is taller than the valley. Yes, I know they're technically infinite at the actual location, but since the hill is taller than the valley, the location of sea level must be closer to the valley. So let's actually figure out where that is. So we said potential is equal to kq over r. So we have the potential from the minus q is equal to the potential from the plus 4q. So if we were actually to draw this out, there's going to be some location right here that will say it's a distance x from the minus q charge. And if this entire distance is d, by segment addition, the remainder would be d minus x. So we can now just plug in. So we'd get kq over x is equal to 4kq over d minus x. And simplifying that, we could cancel a bunch of stuff, and we'd get 1 over x equals 4 over d minus x. And we can multiply to get d minus x is equal to 4x. So d is equal to 5x. So x is equal to 1/5 of d. And we actually could have figured that out in hindsight, that it's 1/5, because since the 4q is 4 times as large, the potential location of 0 must be 4 times farther away. So you actually knew that whatever this distance was, if this is x, the other distance had to be 4x. The field version is actually much harder because there's some squareds to deal with. It's the same idea if the field's canceled in the middle, which they don't, right? Because the fields add. Indicate which region contains a point where the net electric field due to both spheres is 0. Justify your answer by drawing in both regions. All right, let's check. So, plus Q, you are a source. So we are always going to get pointing away. Negative, you are a sink. So you're going to be pointing towards you. So if we look at where the potential sort of the spot for the E field to cancel could be, the only possible place it could cancel is going to be this region. Like we know it's not going to be the middle. And now we have to decide, is it region 1 or is it region 3? Now if we think about it, it cannot be region 3 because the only way it could be 0 in region 3 is if somehow the field produced by the plus q exactly canceled the field from the minus 4. but the -4 is the larger charge. So it's always going to be true that the purple vector is going to be longer than the blue one in this region. So it's actually not region 3. So by elimination, it's going to be in region 1. For that idea. And if you actually work it out, you can see that actually the spot that causes the cancellation, if you work it out, it's just going to be another distance d, sort of right here. Because if we place it right here, this distance would be d. This distance is also d. So if you double the distance, you 1/4 the contribution due to Coulomb's law. So we would get a field, nope, not that. You'd get a field kq over d squared to the left from the plus q, and you would get a field k times 4q over 4d squared from the minus 4q, and those exactly cancel out. So that's kind of interesting that we get that happening. But region 1 would be the answer. Because yes, there is like a possibility, because the fields do point in opposite directions here, but you're always going to have it be true that the -4q is producing a larger field there. Whereas here, if you're really close to the plus q, you're going to get pushed away. And you have to get its distance to diminish enough that it gets pulled towards the -4q. All right, field and potential. Complete the giant flowchart assuming a constant field or force. So we can start from definitions. Electric force, that's just kQq over r squared. Electric field is defined as force per unit charge. So we just take out a charge. So that means we can go backwards by putting a charge back in to the E field expression. Now for the electric potential energy, that's kQq over r. That'll be consistent with how I've been writing it. And potential is defined as energy per unit charge. So we take out a charge from there to get our electric potential. So we got to put a charge back in to get to our energy from the potential. And now what's new with this section is our relationships. So these are definitions that if we have a constant E field, remember the E field points downhill. So E field points downhill in the electric potential. So the magnitude of the E field just tells you sort of how steep is your potential. Because we know that positives accelerate downhill. So how steep is that hill is essentially what the E field is saying. So you can reverse it by saying delta V is E times, I like using D here, so actually we're going to say it's delta V over D. So now we can just reverse that process where we know that we know that this sort of energy change would just be the force times the distance with its relationship to work. So the force would just be the potential energy divided by the distance. Now, of course, there's calculus versions of all of these, like there needs to be some sort of integral and a negative sign here, there needs to be a derivative here. This is just to gain our intuition behind it. So, how does electric potential relate? How does the direction of the electric potential? Oh, bad on me there, there's a typo. Electric field relate to electric potential change? Well, electric field points downhill towards locations of lower potential. So this means the E field is the slope of the terrain, but it also points downhill. So this means you can say that the electric field in a given direction is equal to the negative slope of the potential. Now we'll see how this goes to calculus in our next electrostatics section. And then you can also do this the other way, and you can say that your delta V is equal to negative ED. Because if you travel along the E field for a distance D, I should actually put like a parallel here. If you travel along the way that the E field is pointing, you're going downhill. So this tells you how much you go downhill by. So what's an equipotential then? Well, an equipotential is a curve of constant electric potential. So the electric field is oriented perpendicular to that, since the electric field sends you downhill. So we have two rules to drawing E fields from these lines. E is perpendicular, because perpendicular changes your value the most. And the electric field also points towards lower potentials, because again, just drawing at a right angle actually isn't enough, because there's two vectors you could draw. So you draw the one that points you downhill. So here's our equipotential diagram. Draw the E field line that passes through point A. We want to compare the E fields at different points, and then we want to calculate some things. Okay. E field line that points through A. Well, two rules. We have to be perpendicular, and we have to point downhill. So we do know that it's going to be this. And if we think about what the line is going to do, we can also say the line, it's probably more, maybe like this would be more perpendicular. So maybe the line does something like this. So notice this is at a right angle to all three equipotentials. And at each of these points, it also has to point downhill. So this is 2 volts. This line is 1.5. This is 1, so downhill is going to be this way. Now we want to compare the E field at A and C in terms of magnitude, justify our answer. Well, we said that the magnitude of E can be approximated as the change in potential over a distance. So the closer together your field lines are, meaning this number gets smaller, the higher your E field. So where's the E field stronger? Well, look at the gaps. So here's my gap between adjacent equipotentials looking at A, and here's my gap of adjacent equipotentials looking at C. So the slope is more steep at A than C. And that's essentially what we say. All right, calculation time. Change in electric potential energy moving from A to B, given this charge. Well, electric potential energy change, delta U, is Q times delta V, and we're moving from A to B. So everything should be about V here with your energy relationships. So what is going along path AB? Well, A is on the 2-volt line, and so is B. So it might actually make sense now that we have like the ability to here. We might just want to color in our equipotentials to kind of see. So this would be one sort of level set. So everybody here is at the same potential energy. Everybody on the 1.5 is at the same potential energy. And everyone on the 1 is at the same potential energy. So we can see here that A and B are actually on the same color line, at the same height. So there's no energy change to move along that line. That's just you're sort of walking in a circle of constant height. So it's actually 0. Because VA equals VB equals 2 volts. What's the work done in EVs? So this is just a convenient energy unit by the electric field moving from O to B. So we know that the work done by the E field is actually just defined as the negative of the potential energy change. So we just take Q delta V and take the opposite of that, and we're going from O to B. So what is an electron? Well, an electron is an elementary charge unit, but it's negative. So it's negative E, lowercase e. And what is the potential difference if I start at O and go to B? Well, O is at 1, B is at 2. So if I go from 1 to 2, that's a change of 1, and it's a change of plus 1 because I'm going uphill. So that means it is plus 1 EVs. And we can check the other like work definition for that the sign makes sense, because work is positive from a force if we go with the force. So let's look. If I'm a negative charge, do I want to be pushed towards higher potentials? Yep, I sure do. because positive charges generate high potentials, so the negative wants to be uphill, just like positives want to be going downhill. All right, what's the EVs for a proton moving from A to C? So the work done by an external force. Now, external forces, that does change, that's just the energy change of the system, because that's your energy that comes from outside. So we're just Q delta Ving that, going from A to C. So a proton has a positive 1 elementary charge unit. And if we go from A to C, A is 2 volts, C is 1 volt. So that would be a change of -1. So our energy change here would be -1 EV. And this should also make sense that this is negative, because we have moved our positive charge downhill, so it's at lower potential energy now. That's the extent of things you could be asked with equipotentials, besides maybe like an energy conservation version of this, where you then just set it equal to kinetic or something. All right, a capacitor has 2 parallel plates. Uniform field of magnitude E, ignore gravity. We're saying the top plate is positively charged, and by definition, a capacitor holds opposite charges on its plates. Draw the direction of the E field between the plates. Well, that's easy. Positives are sources, negatives are sinks. Small sphere is placed at the top plate of the capacitor and released, striking the bottom plate with speed Vf. Indicate whether the potential energy of the capacitor sphere system increases, decreases, or remains constant. So we're going to have a sphere. It's positive. Little q apparently. And then it is going to strike the plate. Well, if we think about what's happening, the speed of the particle is increasing. And if your speed is increasing, your kinetic energy is increasing. And kinetic energy, well, kinetic energy must come from somewhere. And in this case, it comes from the potential bank. So my potential bank must decrease to increase the electric bank, or the kinetic bank, sorry. You could have also said that the positive charge goes with the field. So if we go with the field, we're going downhill. And if positive charges go downhill, their energy QV would be lower. So how can we find VF? Well, of course, we'll use our field potential relationship, where we say that my change in kinetic, if I gained kinetic energy, it must have came from my loss of potential from the system. And potential energy is Q delta V. That would be the change there. So notice we actually don't have the potential difference. We're just given this E field and the distance. And that's no problem, because we said that the magnitude of the potential difference is ED. If the E field is constant, which it is between the plates of a capacitor, that's just an assumption we make in here. So we just got to figure out the sign. So we do have a positive charge, and we do have a potential difference ED, and I just look at my picture to find the sign. Am I going uphill or downhill? Well, I'm going with the E field, which points downhill, right? I'm going from plus to minus, so I must be going to a lower height. And that does make sense, because in order to speed up, I better have a positive kinetic change. So since we start from rest, we can just set 1/2 mv squared equal to QED. And we get VF is square root of 2QED divided by M. And this is actually equivalent to that other energy conservation we did from the previous section, because we got 2Q times potential difference divided by M. And what is ED? Well, that is just a potential difference. What's our new VF if we double the E field strength? Well, if we double the E field strength, where does that come into play? Well, that's right here. We're just doubling the E field. So if you double the E field, we have doubled the thing under the square root on the numerator, so we just get root 2 as our factor of change. Pretty straightforward. All right, last electrostatic section, for now at least. What's the smallest unit of charge that can be transferred? We already talked about this. It's actually the elementary charge, which is the electron-proton charge. The elementary charge is 1.6 times 10 to the minus 19th coulombs, approximately. So we have a neutral glass rod. We rub the glass rod with a piece of silk, and the glass gains a positive net charge. And when you're charging things, charge can't vanish. We've talked about that before with the circuit unit. So any charge gained by one object must have gone to the other. So what's the net charge on the silk here? Well, net charge on the silk, if the rod gained plus 160 nanocoulombs, the silk must have lost that many nanocoulombs. So it's going to be negative 160 nanocoulombs for charge conservation. Now let's calculate the number of electrons. Well, the exchange of charge was 160 nanocoulombs, and every electron gives 1.6 times 10 to the negative 19th coulombs. But what is a nanocoulomb? Well, nano is our prefix. That means times 10 to the negative 9th. And now we see the numbers work out intentionally here. So this would be, let's see here. You get 10 to the negative 7, 10 to the minus 19. Those differ by 12. So we get 10 to the 12th electrons are transferred. Indicate the direction of electron transfer. Well, the silk got negative charge. So the rod must have given 10 to the 12th electrons to the silk. So if we were to diagram that out, we would see the rod is just going to give 10 to the 12th E minus to the silk. So that's going to give you a charge deficit of electrons. So you don't have enough electrons to be neutral. So that's positive 160 nanocoulombs, and you are in an electron surplus. So you have negative 160 nanocoulombs. All right, now let's talk polarization. What is polarization? Well, polarization is what happens when you bring a charged object near a neutral one. So electrons are always going to move around to try to get in a better situation. And this doesn't affect the net charge on the system if it's isolated, but it will induce some forces. And this happens to all objects. So this is sort of our go-to picture for polarization, where we have sort of a sphere on a stand, where if we bring like a positively charged rod near it, negatives will tend to group up near the positive end, and positives will go to the other end. So notice there's still no net charge on the system, on the sphere, because they cancel out, right? Plus minus, but there will actually be an attractive force between them because of the inverse square law. Or even though the sphere doesn't have charge, we still get a net force between the two objects because the attractive end would be closer. What is permittivity? Well, electric permittivity is this idea that each material has a different amount that the charges are allowed to separate like this. So air has a very low value of this permittivity, but insulators have a higher value of it. So if we want to increase permittivity, replace any air-filled things with dielectrics or insulators, so we get this effect to be increased as opposed to what air allows it to do. Here's a common misconception question. A ball hangs from a string. It's attracted to a charged rod. What can be said, if anything, about the ball and the net charge on it? So people think, oh, well, if the ball is attracted to the charged rod, the ball must have this the opposite charge. Like if the rod is positive, oh, it's attracted to positive, so it must be negative. That's actually not necessarily true, because we just said neutral objects polarize. So all that can be said is that the ball doesn't have the same charge as the rod, because repulsion can't be faked. So it could be electrically neutral. So we could totally, like, this is definitely a valid scenario that could exist, right? We definitely could have something like this. Like, that's totally possible. But we could also just as easily have something like this, where we still have a positively charged rod, but we could actually have a neutral ball where the charges polarize in there, where we get negatives on one side and positives on the other. So just be on the lookout for that fact that just because we have attraction doesn't mean we absolutely know the sign of the charge. It actually only tells us that it can't be negative if the rod was positive. Charging by induction. What is charging by induction? Well, charging by induction is this sort of process where we can start with these neutral objects. We start with these neutral objects, and then if we put a charged object near them, this is sort of using polarization to charge something without actually touching. So if we put a positively charged rod near these two spheres, the polarization is going to make it such that the sphere closer would have a net negative charge, and the sphere farther away would have a net positive charge due to this rod. Notice nothing has touched. That's the key to induction, is that nothing touches. And then what you do is while the induced charges are still happening, you separate the spheres, so you have successfully given two objects a net charge without actually touching them to anything. So no charge was transferred from the rod, yet you get a net charge. So here on each of these spheres, we initially had Q equals 0 on each, but now at the end you do have two charges. They still do have like equal and opposite charges, like they will still cancel, but that's induction. What is grounding? Grounding is just this process of connecting a conductor to the ground or just some large object that will just accept any net charge. Usually we do just think of it as the ground itself. So for example, if I have a negatively charged sphere and I ground it, we can just have this wire sort of serve as an infinite dumping ground of electrons until it's happy. This also allows you to get a net charge if you bring charged objects near it, as we'll see here. All right, let's look at these two metal spheres described below. Sphere X is positively charged, sphere Y is neutral and grounded. So we have this scenario where we have a positively charged sphere, and then we have a neutral sphere. First, let's say we brought the spheres together, then we cut the grounding wire. What would happen to the charge on sphere Y? So if we bring the spheres close together, what is that going to do? Well, I've brought a positive near here. So that's going to try to polarize these charges. So what that's going to do is that is going to bring electrons from the ground onto sphere Y, because it's going to try to suck up electrons from the ground. And if I just cut the wire at this point, well, the electrons that have been brought onto the sphere from the ground are just kind of stuck there. So sphere Y is negatively charged. But in scenario 2, we ground the wire. We cut the wire, then we bring the spheres close together. So if we do that, we get this scenario where the charges in the sphere are going to polarize or separate. But if you cut the grounding wire beforehand, there was nowhere for these charges to go or come from. You couldn't get these extra electrons if the grounding wire was cut. So we actually get an electrically neutral sphere, but it is still polarized. So kind of tricky looking at our language here. All right, how do conductors behave? Well, conductors are defined as allowing electrons to move freely. So if there was an electric field inside the conductor, the electrons would be moving. So in electrostatics, which happens very, very quickly, we say Well, the electric field must be zero inside any conductor, because if not, the electrons would be still moving around until the field becomes zero. That's what a conductor does. Like, there's no way the field couldn't be zero, or else the charges would still be moving around. And if the charges aren't moving around, there must be no forces on them. So E must be zero everywhere. So as a consequence, all charges reside on the surface, because that E field that initially repels them all, they're going to try to get as far away from each other as possible. And where's that? That's going to be at the surface. They're maximizing their distance to each other. But we also know that electric field tells you how the potential changes. So if E is zero, the potential can't change, which means the potential is constant and usually not zero. It's just some positive or negative number everywhere. So this means conductors are equipotentials. So the potential is the same everywhere inside and on the surface, because E is zero, so the potential can't change. So if we have a positively charged sphere that's outside of a neutral conducting shell, we can do a couple things here. We can draw some field lines, we can label an equipotential surface, and we can rank some things. So first of all, we know, I'll actually do part 2 first, because anytime you have a conductor, we should write these things. E equals 0. V is constant. So what that means is that this is an equipotential. It's an equipotential surface right here. So as a result, this actually means that there's no electric field inside, and the electric field outside has to be perpendicular. So if we draw some field lines here, we can do something trying to show that at all points we get perpendicular to that surface at that right angle. So what this tells us actually is that this would be our high potential over here, and whatever direction this is downhill because of our source and sink rule. So now we're going to do our ranking. Rank the E field at each of the indicated points. Well, we know that E field is 0 at B and D, and it's also 0 at C, because conductors, as a result of this equipotential idea, they also protect you from external fields. So even though we're not actually in a conductor, we're in sort of a cavity region, it's protected from any external fields. This is called conductive shielding. So inside the cavity of any conductor, the E field is also 0 unless if there's any charges there. So being inside a conductor in a cavity hides you from the outside world. Now, if there was a charge here, you would definitely still feel its field. It would do its thing. But being in a cavity protects you. This is why they say, like a Faraday cage or a car, if your car gets struck by lightning, you're technically fine because of that shielding idea. So E is actually 0 at B, C, and D. And it's not 0 at A, right? And we get something like that. Not quite though. I won't put that there. What about the potential? Well, the potential, we know there's also going to be a tie, because an equipotential surface means I could color all of this the same color, since there's no E field to change my potential. So we do know that V is going to tie at B, C, and D, and we got to figure out how that relates to A. Well, the potential at A, notice that E fields point downhill. So what that means is that this region would be at higher potential than this region. So I must be decreasing my potential as I go from A to the conducting shell. So A is actually at highest potential, and you can think of that as, well, A is just the closest to the positive charge. And we should actually write here that this is probably a non-zero constant, assuming you define potential in the usual way. So it's going to be some non-zero positive constant. All right, last one. We connect two spheres. One sphere's radius r and holds charge q. That would be this one. And one sphere has no charge and has radius 3r. The spheres are connected and we reach equilibrium. Once the spheres reach equilibrium, what quantity is the same? Well, remember, these are conductors. So when conductors reach equilibrium, there's no E field in them, which means that their potential must be the same. Because potential is what drives this charge flow. Think of it like batteries. So the electric potential KQ over R must be the same at equilibrium because they have to be equipotentials. So to solve these, we usually do a system. Our first condition is that conductors in equilibrium are equipotentials. So the spheres must match their potentials at equilibrium. So we get this expression. And I think we'll actually simplify this. We'll simplify this a bit. So we're going to get some charge on the sphere of radius r and some charge on the sphere of radius 3r. But they have to match their potentials. So we would get this relationship that the k's cancel, the r's cancel, so we'd get q1 is equal to q3 over 3, which makes sense because your larger sphere, since it has a larger radius, has to pack on more charge to get the same potential. How do we say that the closed system charge remains constant? Well, we just say that when we add up our sphere charges, we have to get exactly the amount of charge that was available to the system, which was Q, capital Q, plus 0. So that's the amount of charge we have to give. So let's solve for the charge on each sphere. Oh yeah, let's change our things to make this easier. Which sphere has radius? The small radius is x. So what is the charge on each sphere? Well, the charge on sphere x, we can just solve using our system. So qx plus qy. Qy is going to be 3 times qx. All I did is I replaced qy with 3 times qx from that equation. So we get qx is just a quarter of q. A quarter of the total goes to q1. And then as a result, if a quarter of it went to x, 3/4 of it went to y. You could pick your favorite equation of the two to verify this, but that's what we get. And then let's find the potential at the center of each sphere. So the potential at x would be kqx over r, which would be k times 1/4 of q divided by r. So it'd be 1/4 kq over r. And then this should match for sphere y when we do kqy over 3y or 3r. So let's check that. Qy we said was 3/4 and 3r, so we do actually get that, right? Because the 3 and the 3 cancel, so we get 1/4 kq over r. And now there's a really sneaky shortcut to this problem that I enjoy, where we could have just said that at equilibrium, we have a charge q distributed over a system of effective radius r and 3r connected to each other. So we get kq over 4r, which is the same result as we expected. So that's a little sneaky solution to that problem. All right, we have done it. That is another long chunk taken out. That is all of our algebra-based applications of electrostatics. So now we'll do algebra-based magnetism next.